Hello there, and welcome to this video. This is the first video in a mini-series which is going to explain the elevation factor. This series is a production of the American Association for Geodetic Surveying. My name is Tom Meyer, and this first video is just background information. So the reason that we have an elevation factor is because land surveyors, upon occasion, will need to reduce distances that they observe at elevation down to the corresponding distance on a reference ellipsoid. The reason they need to do this is because formal mapping systems like the State Plane Coordinate Systems, Universal Transverse Mercator, whatever else, those mapping systems use map projections to take points from the reference ellipsoid to the mapping plane, not points on the surface of the Earth. So when a distance is observed at height, that distance needs to be reduced down onto the reference ellipsoid so then it can be represented properly on the mapping plane. So let's take as an example the Verrazano Narrows Bridge that spans the Hudson River coming into New York Harbor. This bridge is 4,260 feet long, the deck is, and the deck is some 228 feet above mean high water. It has two towers. They're 693 feet tall, and they are plumb. They're straight up and down. If we were to set a total station up on the deck of the bridge, say over here on the left side, and then put a prism at the same height over on the right side, if the total station was set up high enough so that we get above the camber of the bridge deck, then we get a straight line distance from the total station to the prism. If we were to also repeat this observation at the bottom station and at the top, we're going to get three different numbers, three different distances, despite the fact that the towers are plumb. They're plumb, but they're not parallel. We would see that the deck distance is half an inch longer than the distance along the water, and that the tops, the distance between the two tops of the towers, are further apart than their bases by 1.5 inches, despite the fact that these columns are plumb, the towers are plumb. Well, why does this happen? It's because when things move up, they go farther apart. If we could imagine being in the Albuquerque balloon fiesta in the fall, if there was two balloons that somehow rose at exactly the same speed, at exactly the same time, moving exactly straight up. If we had an EDM on one of those balloons and a prism on the other, and we were to measure the distance between the balloons as they were going up, we would see, despite the fact that both of them are going straight up, they would be moving farther apart. The image on the screen explains why that is. It's because, well, the Earth is round. This is, in fact, a demonstration that the Earth was round. If the Earth was flat, that wouldn't happen, but it does happen. We have these two black lines here. They are coming out from the center of, say, a reference ellipsoid. We just have these three concentric circles representing different heights. And the arrows here indicating the places where these black lines are intersecting these circles. And the text says, notice these have the same longitude and latitude. The only difference is that they're changing in height, but the arcs between them are obviously getting longer. We can put hard numbers on this. This example happens to be taken from Albuquerque, New Mexico. And if we had a baseline, so at the latitude of Albuquerque, Albuquerque is at some 5,000 feet high. It's more than a mile high in many parts of the city. But if we had a baseline that was down on the reference ellipsoid at a height of 0, at that latitude, And that baseline was 10 kilometers in length. If we were to move up just 100 meters, notice that that would add almost 16 centimeters to the length of the line. That is not an ignorable change. This is not chump change. That's a major increase in the length of this line, and that's for an increase of height of nearly 100 meters. Albuquerque at some 5,000 feet is between 1,500 to 2,000 meters. If we went the lesser of those two, this line would have increased by 2.352 meters. So this means if I'm up in Albuquerque and I measure a baseline that's 10,002.352 meters long, the equivalent distance on the ellipsoid is exactly 1 kilometer. So this is what the reduction does. It's going to change the lengths of the lines that we measure down to what they need to be so we can represent them properly in our map projection. So we're going to go from ground to the ellipsoid. Here we have a schematic picture of what this looks like. We've got two stations at height, capital A and capital B. We've measured a slope distance, a straight line distance between them. We call it B sub S. Station A is at an ellipsoid height of H sub A. Station B, an ellipsoid height of H sub B. If we take A, and we look at the corresponding point on the reference ellipsoid, so we come straight down, that's at point A, lowercase a. Likewise, capital B comes down to point lowercase b. And what we want to do, or the goal here, is to reduce the slope distance, which is a straight line distance, to the arc that we see here, d sub e. This is a distance along the ellipsoid. These are different kinds of curves. We're not going from a straight line to another straight line. We're going from a straight line to an arc of some description. And how would this happen? What curve are we talking about? Well, the way that it's going to happen, let me show you. We've got a little algorithm for it here. Let us start. Suppose it was the case that we knew the coordinates, the latitude, longitude, height of both A and B. Now, in practice, you won't. The whole purpose of doing this mapping is generally, if we're occupying A, excuse me, if we're occupying A, the reason we're doing this is to determine the point B. But right now, just to explain the background geometry of what it is we're doing, let's just assume we know them both. So I'm going to take those coordinates in longitude, latitude, and height, and I'm going to transform them into geocentric XYZ coordinates so that I can represent the straight line from A to B easily in the XYZ coordinates. So then, for all of these points from A to B, pick any particular point. The corresponding point down on the reference ellipsoid is the point that is, if you will, straight down, where it has the same latitude and longitude as this point in the middle of this straight line, but the ellipsoid height is 0. And so that's the algorithm. For all of the points, all infinite points between A and B, we've got them in XYZ coordinates, convert those back into longitude, latitude, and height, and simply set the ellipsoid height to 0. That will be the curve from lowercase a to lowercase b. Such a curve has a name. It is a thing called the curve of alignment. Now, the curve of alignment is not a particularly simple curve. The algorithm is quite simple. The way to convert this straight line to a curve of alignment, that's quite simple. But what we need is the length of that curve of alignment. We need to know its arc length, and that is not so simple. The formula for a curve of alignment isn't a simple formula. We would have to use calculus on this complicated formula to be able to integrate it across its lengths to determine the arc length, and analytically integrating that formula is, I don't think anyone's ever done it, and it's a complicated enough formula that I question whether there would be a closed form formula for that expression. So I suspect instead what we would have to do is integrate it numerically. This would require writing a custom program. This is very complex, but in full rigor, conceptually, that's what we're doing. We're trying to come up with the length of this curve of alignment. Well, is there an easier way? If we simplify the problem by, instead of using an ellipsoid, suppose that just for this one horizontal distance, we were to substitute the ellipsoid with an appropriately sized sphere, an Earth-sized sphere, and a sphere whose radius was chosen to match that of the ellipsoid at this point. Well, that simplification opens up a world of possibilities for us. Going from the ellipsoid to a sphere makes things much easier. So there's actually a number of different ways to do this. We could take the slope distance and we could reduce it directly either to the equivalent circular arc. Now we've gone from a curve of alignment to a circle because the projection of ds down onto a sphere is going to give a circle, not a curve. Well, it is a curve of alignment, but that curve of alignment will be a circle on a sphere. So there's formulas that would let us take ds directly to dE. There's also formulas that let us go from ds directly to the chord between A and B. We'll discuss those at the very end of this mini-series. But for now, what we're going to do is take a look at reducing a horizontal distance, dH, down to dE. This is the one that's going to lead us to the elevation factor. So under the assumptions that we're dealing with a sphere instead of a ellipsoid, we have a single value r for the radius of the sphere that we've chosen. There's an angle theta between A and B. And we're going to pick the horizontal distance here is going to be at the average height between A and B. So since d sub h is a circle, it's a segment of a circle, well, the formula d equal r theta tells us everything that we need to know. In particular, what it would do is allow us to solve for this angle theta. We don't know what the other angle is. We would need to solve for it. But if we're going to say that the horizontal distance from A to B is d sub h at the average height between A and B, well, we know what the height, the radius out to d sub h is. It's the radius of our sphere plus the average of HA and HB. So we know the radius. That would allow us to solve for theta. Similarly, by exactly the same logic, we can apply that logic to d sub e. This is d sub e is what we're trying to find, but it's the same theta subtending from little a to little b. So up here on the right, we've got d sub h. The horizontal distance is r plus h bar times theta. We can solve that for theta, just a little trivial bit of algebra. Just divide both sides by the r plus h bar, and we see theta is equal to dh divided by r plus h bar. For the curve on the ellipsoid, it's dE is equal to r times theta. It's theta in both cases, so we solve both equations for theta, set them equal to each other, and after a little bit of manipulation, we come to the formula here that the distance on the ellipsoid that we want is equal to the horizontal distance that we measured times the radius of our sphere divided by the radius of the sphere plus the average horizontal height, or the average ellipsoid height.
Yeah.
This multiplicative term, this term that's multiplying the horizontal distance, is called the elevation factor. That's where that formula comes from. So as the series progresses, here will be the order of the presentations. The next presentation is a theoretical background presentation on what is curvature as a mathematical concept that will lead us to radius of curvature. And we need radius of curvature in our formula. On the previous slide, the r here, well, where does this value come from? It's going to be a thing called a radius of curvature, and so we'll see what does that term actually really mean. Following that, we'll take a presentation, a review of the basic geometry of ellipses and the fundamental formulas that we're going to need thereafter. So this will be a little bit theoretical, but mostly practical. Here's how you compute the various values that we're going to need in order to move to the next presentation, where we take a look at what are the various radii of curvature that we use in geodesy. There's a fair number of them. And we need to know how to calculate these, because the value of r that we are using in our formula for the elevation factor depends upon several different radii of curvature. So now that we can compute all the radii of curvature that we need, we can then go on to the elevation factor itself. We'll present some practical computations. How do you actually use the elevation factor? It's very simple. You just multiply it times your horizontal distance, and give some examples of the elevation factor in practice. And then finally, we'll close out with a presentation that doesn't use the elevation whatsoever. If someone wanted to use direct reductions to the ellipsoid that would not involve this hypothetical horizontal distance at the average height between the stations, no, we could go from something we actually measured with our EDM, the slope distance, directly down to the ellipsoid and not have to do the approximations of the elevation factor. And is that something that a practicing surveyor would necessarily want to do? Well, we'll take a look at what difference, if any, that makes. All right, so here's a list of the references for the various papers that I cited throughout this presentation. That concludes this one, and we will see you in the next.